Hey, this is Mike Butler from Process Engineer School. Today we are going in deep. We're talking about K-tron loss and weight feeders explained. This comes from a viewer request to understand the K-tron manual better. He sent me 3 pages from the manual and he just wants to understand it better because they can be a little bit confusing. If you're trying to understand loss and weight feeders for the first time, I recommend going to another video that I created called Loss and Weight Feeders, and it's a little bit higher level and goes into some real world examples. Today we're digging through the manual, which I think is fun, but if you're seeing it for the first time, it might be less fun. So, I'm literally going to go line by line for the first little bit, and then I'll go paragraph by paragraph, and there is some pictures, so it's not that boring. As the name implies, operation of a loss and weight feeder is based on the measured loss of the feeder weight over time. Boom. Seems kind of clear. So just to give you an idea of what is loss and weight, it's looking at the loss of the weight of the feeder over time. It's in contrast to gain in weight, to a gain in weight strategy. I've had times where we are making a batch in a big tank where we're adding in multiple liquids and powders, and we want to know how much is in the total batch, and we'll look at the weight before the batch is made and also ongoing as the batch is being made, and that difference is called the gain in weight. It's how much is in the tank. So that's a gain in weight strategy as opposed to a loss in weight strategy, which we're talking about here. The weighing device measures the weight of the feeder, the storage hoppers, and the material at a given time. The weighing device, I've heard called weigh cells, weight cells, load cells. They're all the same thing. Typically there's 3, sometimes 4 load cells, weigh cells that are constantly measuring the weight of the feeder, the storage hoppers, and the material. So around the feeder, I'd hope you would see some breaks in the piping, some flexible tubing in the piping, and that is the isolation between the K-tron feeder and the rest of the device, because we don't want to be measuring the weight of a tube that is bolted to other equipment. The controller can continuously monitor the weight of the system and determine the mass flow as the first derivative of the weight with respect to time. The controller that they're referring to is the local K-tron controller. It's in contrast to the control system that is communicating with the K-tron controller. I worked for Procter & Gamble for 10 years, and their strategy is to invest a lot of money into automated equipment. In our case, we would always use a control system such as Wonderware. It was in Wonderware that we would actually be reading most of the information that came from the K-tron. It's only during troubleshooting that we would actually go troubleshooting and setup that we would go to the K-tron local controller. But their point is that the controller can continuously monitor the weight of the system, and that is what's needed to understand the loss in weight. The chart below shows the weight of the entire system, which is the feeder, the hopper, and the material. The hopper is where the material is stored before it comes into the feeder. So I'm going to be reading from the right. I know it's small. I'm going to be pointing to the picture on the left. The desired feed rate, represented on the diagram as a series of small steps, is entered on the controller. Like I said, the controller, we would always put the feed rate or the percent in the recipe in the control system, and the control system would break that down and send the actual pounds per hour or kilograms per minute to the K-tron controller. Also, a point of exactly what format we're putting it in. It depends on if the system is a continuous system or a batch system. A continuous system is one where you're constantly adding in material, multiple materials, having them go through a static mixer or getting them mixed up in as they go along, and that it only stops when the downstream equipment has a failure. Versus a batch system, picture a big tank that we're filling with different ingredients, some powders, some liquids, or all liquids, all powders, and then it gets mixed up. The additions stop as that batch is being used, and then the equipment will start back up again when the next batch is needed. A step is defined as the difference in weight reading in a fixed time interval. The incremental time interval is referred to as the update time. The slope of the step is a direct representation of the set point. So they are talking about this diagram. In this example, the big bold line is the weight of all of the equipment, which includes the material. There is a refill, and the equipment starts running again at a new set point. It says 720. It doesn't matter what the units are, whether it's pounds or kilograms. And this is the weight of refill complete, and this is the weight of the refill required or refill request. But as I was saying, this part of the manual is referring to this discrete nature of the K-tron, where the actual weight is decreasing continuously in a solid line, but the K-tron is only measuring on a set interval. So in this case, they're saying it's going to measure every 1 second, and if you divide the 360 pounds per hour into a 1 second interval, you expect to see a 0.1 pound of weight loss. So it measures the weight here, and it measures the weight here. So it assumes it's just saying that there is no further measurement as this line is horizontal, and then it updates during the next measurement. We will talk much more about that. The slope of the step is a direct representation of the set point. Increasing the set point will increase the average slope of the line through the steps. Decreasing the set point will decrease the slope of the line. The steps are magnified for clarity, and in reality are so small and exist for such a short time that the weight appears to be changing smoothly. The step-like nature of the set point ramp results from the accurate, discrete, digital nature of the control logic. So they're talking about slope in this part, where the slope here is 360 pounds per hour. The slope here is half that at 180 pounds per hour. So you can see that the slope here is more negative, the slope here is less negative. They're saying that this is a greater slope and this is a smaller slope. They mean magnitude, they're ignoring the negative sign. The steps here are magnified for clarity. When you zoom out, you're basically seeing a continuous flow rate. And the step-like nature of the set point just comes from the fact that they have to plug this into an equation. They have to have time 1 and time 2, and then measure the weight difference between those two times. And so if you zoom in far enough, it looks like a looks like a series of steps. In reality, the computer does the calculation of mass flow, and it is as follows. The mass flow is equal to the weight at time 1 minus weight at time 2, divided by the time step, which is your time t1 minus your time at t2. So it's your time interval, which in the previous example is 1 second, and the weight difference in the previous example was 0.1 pounds. Beginning at t1, note that the feeder's hopper is filled with material since the measured weight is WRC, the weight at refill complete or refill maximum. As the feeder discharges the material from the scale, the measured weight will ramp down. At some point, T2, the weight reading will be taken again and then mass flow computed as shown above, subtracting the weight values and dividing by the time interval. So T1 is when the refill is complete, which is right here, and then it says at some time later it says T2, so it doesn't actually show what it is, but you don't need to. You can imagine it here. This could be T1 and this could be T2. At T1, the difference in time, so the difference in weight between T1 and T2 is 0.1 pounds, and the difference in time between T1 and T2 is 1 second. The controller will compare the actual weight ramp to the set point and adjust the discharge rate to minimize the error, which is also known as the difference. At the point labeled WRR, or refill min, a request to refill the hopper is made while gravimetric control is terminated in favor of volumetric control. So they must have previously explained the difference between gravimetric and volumetric. Gravimetric is when the screw speed is being controlled by adjusting for this difference. Volumetric is when it makes its best guess as to what the screw speed should be in order to meet the right set point, and it just runs at that screw speed. And the reason why it has to go into volumetric mode is because during the refill, you're not getting a loss in weight, you're actually getting a gain in weight. You're not actually able to calculate the set point. This would be a simple control scheme if the hopper were of infinite size and the weighing sensor always gave an accurate weight. In the real process, the hopper has a limited capacity and must be refilled while the feeder is continuously running. The weighing device is also subject to inaccurate reading due to vibrations, material motion in the hopper, and outside influences on the scale. The sequence of events that occur during refill of the hopper will be outlined later in the control section. The possibility that the weight readings may not be true readings is a major concern. If the set point is 360 pounds per hour and the incremental time between readings is 1 second, the weight loss in that time period would be 0.1 pounds. Any inaccuracy of the scale can produce large errors in the measured weight loss. If, for example, the maximum error in a measurement is plus or minus 0.5%, and the two consecutive true weights of the system are 101 and 100 pounds, the measured weight difference can be anywhere from 2 pounds to 0 pounds. So if the true weight loss went from 101 to 100 pounds, it might have measured the first measurement, instead of measuring 101, it might have measured 102 because there's a little bit of bounce in that signal. And when the weight was actually 100 pounds, it might have measured 101 or might have measured 99. So if you look at each step, there's going to be some inaccuracy, but the K-tron controller is going to level out that signal over time, and it does some averaging to take out that bounce in the signal. A measure of the amount of noise of a system can be characterized by the signal-to-noise ratio. The signal is defined as the weight loss in the time period, and the noise is the amount of possible error in the measurement. Alright, so that is it. That is a kind of boring explanation of the manual, but it is important. If you can master this, you will come off as a rock star to your peers, because a lot of people just don't really fully understand the details of how a K-tron feeder works. So if this helped, please give me a thumbs up, please subscribe to the channel, and write in the comments if you have any further questions. I created this video because of a question that came from a viewer. If you have further questions, please write them in the comments. Alright, I'll see you in the next video. Thanks, bye.